We're on the second part of Unit 2D. So this is the homework from the first part. You could stop it and look at it if you need to see the answers. Okay, so this one's kind of a weird lesson. So this is analyzing departures from linearity. So sometimes the data is not linear. Well, you may or may not realize this, but we only do linear regression when we do regression. So we almost need the data to be linear. So how can we straighten out the data? So this is kind of a weird kind of place we're at, where we want to take the data that's there and make it straight-ish. It may not be perfect, but something straighter than a curved line there. So sometimes you can do that. You can see this plot is clearly nonlinear. But when you take in this case, the log of the x value, look what happened, right? We linearized the data. It looks somewhat straightish. I'd say that, a linear fit would probably be a good fit for that one. So now the x value is not income, it's log of the income. The y value is just life expectancy in years. So if you look at again, the straightened out data, so notice what it says for x, not income, it says log of income there. So we're taking the log of the income in order to straighten out that data. But now we have nice linear data. We can do lots of stuff with that. Good. Here's a scatter plot that is also nonlinear about ocean rockfish. Length and weight there. So maybe if so it's not just taking the log of one or both of the variables. Sometimes you take the log of both variables. That works sometimes. Sometimes you try other things, like in this case, I think they did the cube root of the y variable, and look what happened. It kind of worked there. So sometimes you have to try stuff, kind of figure out what might work in that setting. This is kind of curved up, and you think, maybe a square root or a cube root would work there. And now we're comparing it to the cube root of y, which is the weight there. We do all our linear regression on there, we get all of our stuff, and it works. And again, our equation is not the predicted weight, but the predicted cube root of weight, which is the y variable there. And then the rest of the equation is the same. You'll see that that will come into play as you're solving for some things later in the lesson. So this one looks linear, but of course, if you look closely, it doesn't say weight and length there. It says the log of weight and the log of the length. So they took log of both of them and it straightened it right out, right? Looks pretty good. Oh, so they say now let's make a prediction using this equation. So this is not so easy, right? So you got to write the equation. So let me get that here just a second. So our equation would be the y hat, which is, in this case, is the log of the weight equals the y-intercept, which is negative 1.9-ish, pretty close to that, plus 3.05 times. This is not just your x, it's the log of length. So log of the length. Okay, so it says in the problem, we have predict the weight of a 36 centimeter long Atlantic Ocean. Okay, so we're going to predict, so we're going to plug in 36 right there, right, for length. So we're going to predict the weight, right? So we're going to predict the weight given a 36-inch length. So get your calculators out. We're not going to use math to solve this. You could if you wanted to. But for the rest of us, we're just going to solve this. This is stats class. So algebra, solve. So we're going to take the log. So if you hit the log button there, which is, here it is. Log base 10. So we're just going to leave that blank of weight. I'm going to put W just so I have a variable. Equals negative 1.9 plus 3.05 times the log again, base 10, we can just leave it blank of 36, comma, the variable we're solving for, in this case, that would be W, and it should solve it for us. 702.623. Let's see how we did. So I rounded mine a little bit, but that's pretty good, right? We got 702.1, 702.6, 702.1, 702.6, just a rounding error there. I'm pretty happy with what we got there. And so that's how you kind of set it up and do it. So you have to take into account the fact that both the X and Y variable were logged in the equation, but the calculator would do all the work of solving that for us. To get the predicted weight to undo the logarithm by raising 10. So they use math to do that. They took the log equation, put it in exponential form, and solved it, which is fine, but you don't have to do that. How to choose a model. So there's two things we're looking for, and sometimes you're just trying stuff. Take the log, take the cube root of just X, just Y. Those kinds of things will usually straighten out the data. But how do you choose? Maybe you've tried a couple different things. You're like, what's the better model? So one thing we like is if the residual plot has a lot of random scatter, that's good. That means it's a good linear fit, right? So that makes sense that if the residual plot has a curve pattern, we haven't done our job. Like it's not good enough yet. It's not going to be perfect because it's taking curved data. So, but try for random scatter. That's what we want. If you're debating between two choices and they're really close, look at the R-squared value. So the larger the R-squared value, the more of the variation in Y can be explained by X, the bigger percentage. If the R-squared value is bigger, that's usually better. So those are the two things we might look at when we're comparing and try to figure out which of the models that we tried. We tried some different stuff and see what works. Which model does the best job? So they've got three models here. So they did all the number crunching for us. They even graphed the residual plots. Let's look at the residual plots first. So there's three models, 1, 2, and 3. Of those, which one looks like the most scatter on the residual plot? Well, certainly not number 1. And 3 looks pretty curved as well. The most scattered, I would say, is 2. So I'm leaning heavily towards picking 2. But let's look at the R-squared value, see if that also backs up our claim. So the R-squared value for the first model is 0.822 or 82.2%. For the second model, it's 99.9%. I like that a lot. And then 88.6% for the third model. So the largest R-squared value. So by both metrics, we would choose model number 2. You could probably use either one as your reasoning there. I tend to look at I feel like the bigger thing is the residual plot because, I mean, if it's residual plot's curved, linear fit's not even really a good fit there. So you want random scatter there. So I look at that first, and then I look at the R-squared value. Okay, so for this model, we chose model 2. So we're going to use that to answer this question. This now gets a little dicey here. So calculate and interpret the residual for the trial when the tread depth was 3/32 and the stopping distance was actually 13.6. So the actual is 13.6. The tread depth was 3/32. So let's write our equation here. Again, so let's get our stuff out here. Okay, so on this one, so our equation would be the predicted, in this case, you can look up there, it's at braking distance and tread depth, so braking distance. So natural log, up at the top left, you can see this, natural log of braking distance, brake distance equals, the equation would be the y-intercept, which is 2.9, minus the slope of so it's negative, that's why I put minus 0.269 or 27, times the x value is really the natural log of tread depth. Okay, so we're going to plug in 3/32 into that problem for tread depth, because that's what it says it was, and we're going to get the predicted braking distance. So now get your calculator out. We're going to use the solve command, so menu 3.1, natural log of, let's say B for braking distance, equals 2.9 minus 0.27 times natural log of 3/32, comma, B is the variable we're solving for. So we get the predicted value. Predicted is 34.44. So if you look at the actual was 13.6. So if I did this right, didn't expect that. Let's see what they got. 2.6. They plugged in. Oh, they plugged in 3 there. The tread depth must be measured differently here. So what's it say? In 1/32 inch increments. So it's measured in increments. So they're putting the increments there. So I did not read that when I first saw this problem. So we're going to change our solve command. This should fix it. So what's nice is, so instead of 3/32 there, we're going to type in 3 because it's measured in 1/32 increments. So this is 3 of those increments. And so we get 13.5. That makes more sense. I knew there was something suspect to that. So this should have been plug in 3 there because it's measured in 1/32 increments. And so we get 13.5. So minus 13.5 is 0.1 approximately. Would be our, and it's positive. So that's a positive residual there. And so they get 13.57. We got slightly different. I guess I'm rounding too much probably there. 0.5, yeah, because we got 0.51 essentially. If I hadn't rounded quite so much, you can see they did not round as much as we did. We would have gotten the same answer there. I'm not worried about the rounding error there. Okay, so when tread depth was 3/32, the car traveled 0.03, or in our case 0.1 is what we got. Car length further or farther than the distance predicted by the model using X. Okay, so that's the lesson. Let's just try a couple of problems just to practice some more. So predict the number of nesting pairs of bald eagles in 2000 using this model. Okay, so let's write our equation. So we start with the predicted y value, which would be the natural log of nesting pairs equals the y-intercept, which is 5.632. I won't round as much this one, plus 0.079 times the x value, which is years since 1960. Okay, so it says predict the number in 2000 since 1960. So that's 40 years from 1960. So I'm going to plug in 40 there. So I'm going to get my calculator out and solve this guy. So menu 3.1, natural log of n for nesting pairs equals 5.632 plus 0.079 times 40, comma, the variable we're solving for, which is n for nesting pairs. So we get 6581 6581.38 nesting pairs. That's right. So they used math to get that. They put it into exponential form from natural logarithm form. You can do that if you want to. Which model does the best job of summarizing the relationship between radius and volume? Explain your reasoning. Okay, so, definitely model 2, right? So look at this. I haven't looked at the R-squared value, but just looking at the scatter, it's more scattered, so it's a better fit for model 2. R-squared is 1. Oh, that's perfect, right? That's better than 0.974 or 0.976. So it would be model 2. So that's the one that has log of volume and log of radius. So now use that to calculate and interpret the residual for the observation when the radius is 5 and the volume is 80. So then you would get your, this out and go, okay, let's write our equation. So our equation would be the predicted, let's see, so log radius is the x value. So this would be log of volume equals the y-intercept of 0.486 plus 2.021 times the x variable, which is log of the radius, and then we're going to, the question is, interpret the residual for the observation when the radius is 5 and the volume is 80. So we're going to plug in a radius of 5 there to find the predicted value here. So we're going to get our calculator out again. You can see that we do this a lot, many 3, 1. So log of V, I'm going to say, equals 0.486 plus 2.021 times the log of 5. And we're say comma, we're solving for V there, 79.11806. So 80 was the original, or the actual, I should say. So you subtract those guys. I think you get 4918, I'm guessing. I think I did that right. Let's see, 0.8194. Let's see what we had. So 79.25. I wonder if they rounded. So 79.25. You get 79.18006. I know we did ours right. Our equation set up correctly. I have a feeling that's just a rounding error, and so I'm not worried about that. You show your work. You're good on that one. So 0.8194. So it's a positive residual. So when the radius is 5 meters, the volume of spill is 0.8194, more or greater than the volume predicted, because it's a positive residual. So it's an under prediction there. That's the end of the lesson.